Okay, sorry for the confusion in the last video there. This time here, you do have to factor out, first of all, a common factor, but when you do, you'll be left with the difference of squares that can be easily factored. Go ahead and try that now. Okay, so our GCF here is just 2. Factor that out and you're left with 25x squared minus 4y squared, a difference of squares, which means to factor that this bracket part here is really easy. The square root of 25x squared is 5x. Square root of 4y squared is 2y. Write that in both places. 2y. Put a plus sign there, a minus sign there, and you're done. Easy breezy. Oh, darn it, I did it again. Okay, so that's difference of squares. Nice and easy. Let's look at the next one, which is a perfect square. Okay, so a perfect square is where we take a binomial and we square it. So x plus 4 times x plus 4. If you do the binomial expansion, you get x squared plus 8x plus 16. Let's look at a couple of other ones and see if you can find a pattern here. Okay, so there's 3 examples of perfect squares, and we have to first be able to recognize them. Not as easy to recognize as difference of squares because that was really easy, obviously, but there is a way to recognize perfect squares. You'll notice, first of all, that the first and last term are again perfect squares. And obviously you can see the connection here between the square roots rather, and the binomials that we squared to get them. The hard part is trying to figure out this middle term. How do we know when this is the middle term is going to tell us when this is a perfect square or not? So to do that, just look here how we got that number. We went x times 4, which is 4x, plus 4 times x. Or in other words, x times 4 times 2. Or x times 3, which is 3x, times 2. Or 2x times 5, which is 10x, times 2. And so if you can take the square root of the first and last terms, multiply those together, and then multiply that by 2, if it equals that, then that is a perfect square. Let me show you an example of some that are perfect squares and some that are not to demonstrate that a little bit. Okay, so looking at this top example here, okay, so the square root of x squared is just x. The square root of 25 is 5. X times 5 is 5x. 5x times 2 is 10. 10x. So this is a perfect square. Let's look at the next one. The square root of 4x squared is 2x. The square root of 9 is 3. 2x times 3 is 6x times 2 is 12x. That is also a perfect square. This last one here, I haven't put a number in there, but we know what the perfect square should look like. In other words, the square root of 16a squared is 4a. The square root of 49b squared is 7b. So 4a times 7b is 28ab times 2 would be 56ab. So if there's anything besides 56 there, like 58 for example, I can't factor it as a perfect square. That doesn't mean it's not factorable necessarily, but it can't be factored as a perfect square. So it's a bit more difficult to recognize these, but once you do, then factoring them is just as easy as factoring a difference of squares. Because I know, for example, this up here, the square root of x squared is x, the square root of 25 is 5, so I go x plus 5 times x plus 5. Done. Or I can just say x plus 5 squared. Like that. Okay? This one here would be 2x plus 3 squared. This one here, if it was 56 that was here, like that, I could just go, well, it's 4a plus 7b squared. Done. And so factorable like that. So I'm going to give you one example for you to try in the next video. I'm going to give you 2. And one will be a perfect square, one won't be. And you can factor the one, well, factor them both if possible. And we'll see how that works out for you. So let's go to the next video here.